The part R has this upper bound should be right. This upper bound property. Because R doesn't have this upper bound. The part.
This part?
Yeah.
You mean the real line doesn't have?
This
Really?
Yeah.
R doesn't have real this upper bound property?
This upper bound you should add property.
Yeah. Oh, here. Yeah. Property. Yeah. Property. You mean add it here?
Yeah.
Okay. Yeah. Sorry about that. Can I erase it? Yeah, sure. Up here. Okay, so in these questions, we're working in the Euclidean space. Let me make it clear here. Right, so in this case, we know that the sequence of xn converges to x, and the sequence of yn converges to y, right? And we want to prove that the limit of the sum of these two sequences converges to x plus y here. So the way I did it is that first I prove a small lemma here. I show it that if we add another terms to both point here, the distance is not going to change. And that is by definitions. We just write it down and we can get it directly. Okay, and we are going to use this lemma later. Okay, then follow the definition of convergence. Okay, we pick any epsilon larger than 0 here. And because we know the sequence will converge, the sequence of xn and the sequence of yn will converge. Right? So that means we are going to find a big N1 here and a big N2 here that when small n pass these two terms, the distance between xn and x will be close enough, which I put the criteria as the epsilon over 2 here. Okay, right? And then, again, this should be smaller. Make a mistake again. Right, and then we denote the big N, which is the larger numbers between this big N1 and big N2. After we pick that, we already know that for the small n, when the small n is larger than that big N here, the distance between these two terms, we can write it, it will be smaller than the sum of these two terms, which is from the triangle inequality, right? And then, by the lemma we just proved, we remove the xn term here, and we remove the x here, then we get what we want, this. And because of the convergence here, so this will be less than, and this will also be less than epsilon over 2. So that means when these two plus together is going to less than the epsilon. And this is the definition of convergence. Right? And we finish our proof for these questions. Questions, or do you need more time? No. Right. Then is the next definition here, which is Cauchy sequence. So a sequence in a metric space is called Cauchy sequence if for any positive epsilon here, there exists a big N in the natural numbers such that when the small n and m larger than that big N, the sequence, the elements within that sequence itself will getting closer and closer to each other. So that is the definition of Cauchy sequence. So the definitions is a little bit look like the definitions of convergence. The differences is that when we define, let me show you directly. When we define the convergence, we need to note where it is converges to, which means that we need to know the small x here. But when we define the Cauchy sequence, we don't need to know where it is converges in advance. Okay, so that gives us some convenience when we deal with some more complicated problem here. Okay. And yeah, so that's what I put it here. And in a metric space, when every Cauchy sequence converges to a limit in the same space, we will call that metric space complete. And apparently, the rational number is not complete, as we can show it in an example square root of 2. So you can construct a sequence that is the, like how to say that, infinitely closer to square root of 2, because actually you can not you can calculate that, but it's like you know the number behind the decimal point if we want to approximate the square root of 2. So you just put that for the first decimals here as the x1, and the second one is 1.41. That this sequence is getting closer to square root of 2. And as you can see that the distance between the any two, how to say that, the distance between any two elements within this sequence, when the numbers of small n's getting larger and larger, the distance between the distance will become smaller and smaller. Okay, and that is the example of Cauchy sequence, but it's not going to converge in rational number because like there's no square root.